Hi guys, here is the video solution for section 2.2, exercise number 3, as requested on the forum. So the problem is let T be the linear transformation from R2 to R3, defined by the following formula. T of the 2-component vector A1, A2 is equal to the 3-component vector, A1 minus A2, then just A1, then 2A1 plus A2. Let beta be the standard ordered basis for R2, and let gamma be this set here. It's a basis for R3. And the problem is then to compute the matrix representation for T with respect to beta and then gamma, beta being a basis for the domain and gamma being a basis for the codomain. And then the last part, if alpha is this other different basis for R2, then compute the matrix representing T with respect to these bases instead, alpha and then gamma. So let's just organize our work. Let's write down the different bases so that we have them organized. Beta is the standard ordered basis for R2. So that's 1, 0, and then 0, 1 is the two vectors. And then the other vector, the other basis for R2 that we'll be working with is alpha, which is given in the problem 1, 2, 2, 3. And then we're also given this other basis gamma for R3. Gamma is the set consisting of the vector 1, 1, 0, and then 0, 1, 1, and then 2, 2, 3. All right, so first, let us write down the matrix representing T with respect to beta and then gamma. So what we need to do is apply T to each of the two vectors in beta, and then write the results as linear combinations of the vectors from gamma. So let's start by applying T to the first element in beta. That will be T of 1, 0. And now we follow the formula. The formula was to take the two components and subtract them to get the first component. So 1 minus 0 is 1. Then the second component is just a 1, the first component, so that'll be a 1. And then the third component of the output is 2 times the first component of the input plus the second component of the input. So that is 2 times 1 plus 0, which is 2. Right, so that is T of 1, 0. And now the point is that we want to write this vector in terms of the basis gamma. So that is, we want it as a linear combination of the vectors 1, 1, 0, 0, 1, 1, and 2, 2, 3. So here, it's not so clear by inspection what those coefficients A, B, and C should be. So we're going to have to solve a system of linear equations in order to figure out the values of these coefficients. So let's see, what does it mean to say that 1, 1, 2 is equal to A times that first vector plus B times that second vector plus C times the third vector? Well, I guess A times 1, 1, 0 is just A, 0, and B times 0, 1, 1 is just 0, B, B. And C times 2, 2, 3 is just 2C, 2C, 3C. And then I can add those three vectors together and get ultimately the vector A plus 2C, then A plus B plus 2C, and then B plus 3C. So if I want this vector here to equal that vector there, 1, 1, 2, then I guess we really just have a system of equations. A plus 2C is equal to 1. A plus B plus 2C is also equal to 1. And the third component, B plus 3C, is equal to the third component of that vector, namely 2. So now there are multiple ways to solve the system of equations. You could turn it into an augmented matrix and do row reduction and so forth. But here, there are only 3 variables and 3 equations. It's not so bad to just do it by hand. So for instance, these two equations, you could subtract the first one from the second one A minus A would be 0, 2C minus 2C would be 0. So we'd be left with B on the left, and 1 minus 1 would be 0 on the right. So then we would know that B has to be 0. Once we know that B is 0, we can combine that with this other equation, and we would find that 3C equals 2, which then implies that C is equal to 2/3. And once we know that C is equal to 2/3, then you can go back to the original equation, A plus 2C is equal to 1, and find that A is equal to 1 minus 4/3, or in other words, A is equal to negative 1/3, I believe. Negative 1/3. Great. So in other words, what we've now done is found the uniquely determined A, B, and C that I can use to write the vector 1, 1, 2 in terms of the basis gamma as a linear combination of the vectors from gamma. So let's update that here. I'm going to erase that A and replace it in red with our value for A, which we found to be negative 1/3. I'll erase the B. B we found was going to have to be 0. Oops. And I will erase the C. And C we found was going to be 2/3. So those three numbers there, those coefficients, negative 1/3, 0, and 2/3, those are going to be the first three entries in the first column of the matrix T, representing T with respect to beta and gamma. The first column, because we've only used the first basis vector of our domain, namely T of 1, 0. So then we're just going to repeat this process, and we'll do it maybe a little bit faster this next time. We're going to apply T to the next basis vector, 0, 1. So we'll follow the formula again. 0 minus 1 will be minus 1. And A1, well, that's just 0. And then 2 times 0 plus 1, that will be 1. So that's the output of T when applied to the second basis vector. And we want to write this as a linear combination of the same basis vectors, 1, 1, 0 plus B times 0, 1, 1 plus C times 2, 2, 3. And again, let's just combine these into a single vector so we can see more clearly what's going on. This is A plus 2C, and then A plus B plus 2C, and then B plus 3C. It's, of course, the same output we had before, or the same linear combination we had before, except now we're trying to equate this to the vector negative 1, 0, 1. So our equations now become A plus 2C is equal to negative 1. A plus B plus 2C is equal to 0. And B plus 3C is equal to 1. We'll use the same trick as before. Subtracting the first equation from the second should leave us with B equals positive 1. Then once B is known to be positive 1, we can say that 1 plus 3C equals 1. So I guess C must be 0. And once we know that C is equal to 0, then one of our original equations, A plus 2 times 0 equals negative 1. So A equals negative 1. Great. So that will allow us to update our coefficients A, B, and C. I'll use a different color, maybe orange. So A, we said, was going to be negative 1. B is going to have to be 1. And C is 0. Those are the three entries in the second column of this matrix. And now, since we've exhausted the basis beta, we've exhausted the two columns that make up this matrix. So we're in a position now to write down what this matrix is. T with respect to beta and gamma is equal to the two column matrix. Negative 1/3, 0, 2/3 down the first column, and negative 1, 1, 0 down the second column. For read left to right, like a normal way of reading a matrix, it's negative 1/3, negative 1, 0, 1, 2/3, 0. Right. So then we're also asked to compute T with respect to alpha and gamma. So we're going to do the same process, except we're going to apply T to each of the vectors of alpha in turn instead of the vectors of beta. So let's do that now. T of the first vector of alpha, that's T of 1, 2. So we will use the formula again. A1 minus A2, that's going to be 1 minus 2, so that should leave us with a minus 1. And then A1, well, that's just 1. And then 2 times 1 plus 2 should be 4. And again, the objective is to write this as a linear combination of the vectors from gamma. Well, they're the same vectors as before. So 1, 1, 0 plus B times 0, 1, 1 plus C times 2, 2, 3, which is really just the same as A plus 2C, A plus B plus 2C, and B plus 3C. So in order to figure out the values for A, B, and C, we're trying to solve the system A plus 2C is equal to negative 1. A plus B plus 2C is equal to 1. And B plus 3C is equal to 4. Following the same method, subtracting the first equation from the second, B is equal to 1 minus negative 1. So B is equal to 2. Once B is equal to 2, we can determine that 2 plus 3C is equal to 4. So this implies that 3C is equal to 2. So C is equal to 2/3. And then we can go back to the equation A plus 2C is equal to negative 1 and find that A is equal to negative 1 minus 4/3. So I guess A is equal to negative 7/3. So let's again go back and sort of update these A, B's, and C's. A is negative 7/3, we said. B is 2. And C is 2/3. So those are going to be the first column. Those three numbers are going to make up the first column of this matrix, T with respect to alpha, then gamma. And finally, we will do one more calculation here. T applied to the second vector from alpha, that is 2, 3. So doing the calculations, let's see. T says we subtract the two numbers to get the first entry, so 2 minus 3, that's a minus 1. The next is just the first entry, 2, and 2 times 2 is 4, plus 3 is 7. We want this to be A times 1, 1, 0, plus B times 0, 1, 1, plus C times 2, 2, 3. Again, because we're writing down the matrix for T with respect to alpha and then gamma, we're writing the results of T applied to alpha in terms of the vectors from gamma. And that amounts to solving systems of linear equations. A plus 2C, A plus B plus 2C, and b plus 3c. So that means that a plus 2c is supposed to equal -1. A plus b plus 2c is supposed to equal 2. And b plus 3c is supposed to equal 7. So subtracting the first equation from the second, b is equal to 2 minus -1, which is 3. So then we know that 3 is equal, 3 plus 3c is equal to 7. So c is equal to 4/3. And finally, a plus 2 times 4/3 is equal to -1. So that gives us a is equal to -1 minus 8/3. So that should be -11/3. So let's go ahead and update these coefficients now that we know what they have to be. The only way to write -1 to 7 as a linear combination of the vectors from gamma are to have a coefficient of, where's AA is a -11/3 for the vector 1, 1, 0, and then to have a coefficient of 3 on the vector 0, 1, 1, and then to have a coefficient of 4/3 on the vector 2, 2, 3. So that uniquely determines those coefficients, which means that we can then write the matrix itself. The matrix representing T with respect to the matrix alpha and then gamma is again just a 2-column matrix. The first column is -7/3 to 2/3. The second column is -11/3, 3 4/3. Those coefficients coming from the first linear combination that we wrote, and then the next linear combination that we wrote. So the matrix representing T with respect to alpha and gamma is -7/3, -11/3, 2, 3, 2/3, 4/3. Hopefully that is helpful. I apologize that this is coming in so late, but it's the first opportunity I've had to make the video. So I will announce it to you guys by email, and hopefully you'll get a chance to look at it before the exam. Have a great night, and I will see you early in the morning.